Assalamu alaikum students. Today we are going to discuss the chromatic dispersion and the two parts of chromatic dispersion. The first part we have already discussed, which is the material dispersion, and we have already discussed that no source in the world has the capacity to generate only a single wavelength. The sources generate a range of wavelengths, which is defined by the spectral width of that particular source. And we have already seen that the spectral width of laser diodes, which are used with the single mode fibers, is approximately 1 nanometer or 2 nanometer or even less than 1 nanometer, while that of LEDs, which are used in multi-mode fibers, the spectral width ranges between 50 nanometers to 140 nanometers or even higher. So in this case, the first part of the chromatic dispersion that we discussed was the material dispersion, which was caused due to the variety of wavelengths that are sent over the optical fiber by a particular source, and the longer wavelengths take lesser time to reach the destination, while the smaller wavelengths take more time to reach the destination. What is the reason behind that? The reason is that we have the formula. If we use higher wavelength, the velocity would be higher. So such a wave that has higher wavelength would reach the destination earlier, while the lower wavelength or the smaller wavelength would reach later. The other part of chromatic dispersion is the waveguide dispersion, which is due to the fact that light travels through a waveguide, which is primarily, in this case, is the optical fiber. What happens is that the mode field diameter of the wave is larger than the physical core diameter of the fiber. So a certain part of the wave, approximately 20% of the intensity of a light, travels through the cladding, and it is not contained within the core. So what happens is that 80% of the light passes through the core, which undergoes or has to cross a higher refractive index path, which makes its velocity lower as compared to the 20% part that passes through the cladding, which has to pass a path of lower refractive index. So the velocity is higher. So the part that passes through the cladding reaches the destination earlier as compared to the part that passes through the core. This creates a certain amount of dispersion. Dispersion is the difference between the times of arrival of both of these pulses. The pulse that reaches the destination through the cladding, that reaches earlier, and the pulse that passes through the core and reaches the destination later. So this delta t is the delta t waveguide, delta t wg. We call it delta t wg. We can write it as Here delta lambda is, what is this? This is the spectral width. Which is given in nanometers, while length is given in kilometers, and delta T Wg is the time given in picoseconds. So this gives us the value of waveguide dispersion. Now, what is the combined effect of waveguide dispersion and chromatic dispersion? Actually, we can simply add the waveguide dispersion parameter and material dispersion parameter to get the chromatic dispersion parameter. That is D chromatic is equal to D material plus D waveguide. So it's quite easy to find the value of the dispersion parameter due to chromatic dispersion, right? So in this way we can find out the value of the total chromatic dispersion, right? So the total dispersion in a single mode fiber as compared to a multimode fiber is quite less, because it does not have the intermodal dispersion part, which leaves it with this chromatic dispersion and one more type of dispersion, which is called the polarization mode dispersion, PMD, polarization mode dispersion. What happens is that when the light travels through the fiber, it has its electrical field intensity vector in one direction, while it has another part of the same signal orthogonally placed. When both of these pass through the fiber, they might undergo two different refractive indices. Reason being the fact that it is possible that within the core, a certain part might have a certain value of refractive index, while another part might have another value of n. So if the electric field intensity, it's two polarized parts which are orthogonally placed, they pass through these two different different materials or two different refractive indices, they would reach the destination with a time difference. This time difference is called the polarization mode dispersion. You can see this polarization mode dispersion in case of in your book at page number 176, and the value is polarization mode dispersion does not depend upon the length of the fiber, while it depends upon the spectral width, but not directly. It is proportional to the square root of the spectral width, while the other parameter is the parameter of polarization mode dispersion, which is d PMD. Now let's move back to our um, chromatic dispersion part, in which we have already defined that the total chromatic dispersion parameter is equal to chromatic dispersion parameter due to material plus dispersion parameter due to waveguides. So we can add them up and find the value of total chromatic dispersion. If we see the total chromatic dispersion can also be defined in terms of another formula, which is d of lambda is equal to S naught over 4 into lambda minus lambda naught power 4 divided by lambda cube. To understand this equation, I would refer you to figure number 5.9. You can see here the curves for the parameter for waveguide dispersion and the curve for the parameter of material dispersion, and the resultant of both of these. You can see that the parameter of material dispersion starts from the negative value, and at approximately 1300 nanometers it crosses the zero crossing. It crosses the zero value. After that it moves into the positive domain, while the waveguide dispersion remains on the in the negative domain only. When we add them up, it gives us a resultant which passes through the zero line at approximately 1310 nanometers. That is why we consider 1310 nanometers as the point of dispersion minima. In this case, if we draw a line, a perpendicular line from the point at which this resultant curve cuts the zero line and protrude it to the x-axis, we get the value of lambda naught, which is used here. This lambda naught is the value value of the wavelength at which this resultant dispersion is zero, while S naught is the curve, is the slope of the curve at the point of zero dispersion. At this particular point at which the resultant parameter of chromatic dispersion passes through the zero line, at exactly that point, if we draw a tangent, and then the slope of that tangent would be S naught. If we use these values in this equation, we can get d of lambda. In case of waveguide dispersion, if we consider this as the optical fiber, in which this portion is the core, while uh, this portion is the cladding, then what is the actual shape of the wave or the beam? As we have already discussed, it does not have strict boundaries, rather it follows the Gaussian equation. And what would be the shape? It would be like this. So this portion and this portion have to pass through the cladding, while the central part, it passes through the core. These two parts have to pass through the cladding, which has lower refractive index, so they reach the destination earlier. I will shade it just like this portion has been done. While the portion that passes through the core, it reaches later. I have not shaded it like I have not shaded it over here. So the resultant would be like this. The resultant pulse would be extended or widened like this. So this is the waveguide dispersion. Now to improve or shift the waveguide dispersion, first of all, we will see that how can we have lower dispersion. We have already seen two types of fibers that we compared earlier in our figure 5.8, in which in 5.8 we have checked it, and we have in figure 5.4 the mode field diameter for two different types of fibers. You can see the figure 5.4, which compares the mode field diameters in two different types of fibers. For example, and what were the two different types of fibers? The matched cladding fiber and the depressed cladding fiber. And we have already discussed it, the matched cladding fiber is just like, just has a profile like this, while a depressed cladding fiber is like this. There is a depression just after the completion of the core, and the normal value of the refractive index of the cladding starts after some distance all around the fiber, all around the core rather. So it helps us in improving our our mode field diameter, and the mode field diameter is lowered in this case. Now this was called the matched cladding fiber, while this was the depressed cladding fiber. The matched cladding fiber is also called the conventional fiber. Now we have a requirement to shift the minima of dispersion from 1310 nanometers to 1550 nanometers. How is it done? It is done by altering the index profile of the fiber, basically index profile of the core. For example, we can have a core with not with such a step index. We can have a ramp index. It increases to a certain point, then decreases in a ramp format. It can be like this, or we can have different options for this. We can have like this. In this way, what we get is a dispersion shifted fiber. But when we see our requirements in terms of dense wavelength division multiplexing, we need to have some flattened dispersion flattened fibers, in which we need to have a certain large band of wavelengths through which we can have very low dispersion, and that and such a fiber is called a dispersion flattened fiber. And how do we make it? We can make it by just by altering the index profile. It will be like this. This is one type of profile, and we can also have like this one. You can see this in your book in figure number 5.30. So this gives you some comparison of the two cases. This is dispersion flattened fiber, while this is dispersion shifted fiber. This was the matched cladding fiber, and this was the depressed cladding fiber, in which we had the advantage of lower mode field diameter. Thank you very much.